So my name is Patrick Eaton. I work as part of as an engineer at Google, as part of the Google Cloud platform, and specifically on the Google Cloud monitoring team, where we're working to make the best monitoring solution for applications in any cloud. Today I want to talk about risks, but I'm not going to talk about anything that I'm working on at Google right now. They probably won't let me. Instead, I'm going to talk about my experiences at my previous gig, Stackdriver. So if I'm going to do that, I feel like I should go back to the days where I had a different slide template. This feels a little more comfortable. Let's try this again. Hello, I'm Patrick Eaton. I'm an architect and developer at Stackdriver. Today, I want to talk about taking risks. I joined the company as the first engineer, so I saw it all. And unfortunately, we did a lot of stupid things. Some of it we did due to naivety and inexperience. Some of it we did in the spirit of velocity. And other things, quite frankly, were just plain stupid. By the end, though, I think the Stackdriver engineering team had grown much wiser. And today I want to share some of what we learned. So I promise this is not a product pitch, but you probably know a lot more about Google than you do about Stackdriver. So if you'll let me have a moment to give you a bit of background for this talk. Stackdriver is a hosted service providing intelligent monitoring to help SaaS companies innovate more by reducing the burden of day-to-day operations. We're basically a monitoring and availability tool for applications in the cloud. We're cloud native and cloud aware, which means that we understand what the cloud is and how the pieces fit together. Things like hosted load balancers and on-demand instances and IAM policies. And we're designed for the types of distributed applications that are so typical of what's being deployed in the cloud today. So we understand the design patterns like groups and clusters, and the technologies that are composing it, like Redis clusters and Memcache and Cassandra. What we like to say was that with Stackdriver, you can spend more time on dev and less time on ops. You can focus on the stuff that you enjoy most and the stuff that, quite frankly, probably makes you money. Stackdriver was founded in August 2012 by Izzy Azari and Dan Belcher. We grew to a team of about 25 people based in downtown Boston. About half of those were engineers, and we were acquired by Google in May of 2014, which explains how I get here today with my dueling business cards and dueling title slides. And I still get confused about whether I should talk about Stackdriver in the past tense or not. So let's get on with it. Many software organizations are built to avoid risk. And before Stackdriver, I was in several of these. They had a lot of process and long release cycles. They used a process that many people consider a dirty word today, waterfall. They had separate dev, QA, and release teams, and they all operated at arm's length. And we would throw things over the wall, and we would wait until they would throw things back at us. And we would hardly actually talk to each other at all. Now, in defense of this type of organization, when the cost for mistakes when product reaches the field is too high, it makes sense to spend a little bit more time up front to avoid the mistakes. You know, for example, if you're going to launch a rocket, it makes a little more sense to spend some time up front instead of iterating on that. But it doesn't have to be that way, and it shouldn't be that way for a lot of organizations. And the DevOps way is one alternative. DevOps means a lot of different things to a lot of different people, especially if they're trying to sell you something. My understanding comes from the three ways or the principles outlined by the authors. I hope you had a chance to hear Gene Kim speak today. He's obviously much more authoritative on this topic than I am. But I had built these slides before I saw the agenda, so I'm going to have to talk just a minute about how this fits in. So the three ways. The first way, as you may remember, is a commitment to systems thinking. We want to consider the behavior and performance of the whole system to deliver value. Don't focus on just the silos that reflect the team boundaries. Those silos could be organizational, like dev, QA, support, and sales, or they could be technical, like the front-end team and the back-end team and the database guys and the ops guys. Instead, we need to think of our entire organization as trying to deliver value. The second way is to amplify feedback loops. We're all about serving our customers, and with a tight feedback loop, we can respond to the internal and external customer feedback much more quickly. And then the third way, which is the one related to my talk today, is to embrace a culture of continual experimentation and learning. We should continue experimenting, and we should continue taking risks, and we should continue to learn from that failure. As we are taking those risks, we are also practicing our skills, and that practice leads to mastery of those skills. Then, when our risk-taking fails, that same mastery helps us recover from those failures. This third way even suggests that sometimes we should introduce failures into an otherwise working system. This is a little bit scary and a little bit ridiculous to some, but it's actually really empowering if you think about it, and I'm sure you heard more about that this morning. Now, one thing you don't hear in any description of that or anything that you heard this morning was there's nothing about being rash. There was no riding without a helmet, no jumping without a parachute, and no waterfalls without the barrel. Risk-taking drives improvement, but failure happens, and we're going to learn from that failure. You can't learn from the failure if you're dead. So we have to judge accurately the skills that we possess so that we understand what we're capable of recovering from, and we don't want to push beyond that. Another way to say that is we don't want to overdrive our headlights. I don't know how clear that picture is, but that's the Thank God ledge on Half Dome in Yosemite. And that man in the red shirt is standing on a ledge no wider than the length of his feet. He's looking straight down with no harnesses or ropes. So I think he might have a different view of risk than the rest of us. Hopefully from what you got from Gene this morning and a little bit of what I've reminded you, we've talked about so far having a healthy view of risk-taking. In the rest of the talk, I want to divide it into two pieces. The first piece, talk about how to design systems so that the impact of the failure can be managed. We want the systems that we design to dampen the effects of failure. We don't want the system to amplify the shocks or the perturbations. In mathematical terms, those kind of systems are defined to be chaotic. This part of the talk is more general, but also a little bit more academic in tone. In the second part, I want to talk about how Stackdriver implemented some of these risk-taking ideas, and in particular, talk about it from the angle of being cost-conscious, because we were a startup that was trying to do things on the cheap. This part is more practical, but also a little bit more specific to Stackdriver. I'm sure, though, you'll see similarities to some of the systems that you're working on, and you can take some things on from there. Are there any football fans in the audience? Okay, that's the most popular sport in America, and I think three people raised their hands. So I think we've just validated some gross stereotype about our community there.
It's not a gross stereotype, it's awesome.
So I want to talk for a minute about Super Bowl XLVII. That's 47 if you're not ancient Roman. This was after the 2012 season between the San Francisco 49ers and the Baltimore Ravens. Now, unless you've been living under a rock, even though you're not a football fan, you probably know that the Super Bowl is a pretty big deal in cultural terms. There were 110 million viewers for this game. It was televised in 180 countries. It cost $4 million to buy a 30-second TV ad. And part of the hype leading up to the game, they called it the Har Bowl because the two head coaches, Jim Harbaugh and John Harbaugh, were brothers, are brothers. Some things are hard to separate. So in case you didn't remember it, okay. So Baltimore built a 28-6 lead early in the third quarter. Then San Francisco scored 17 unanswered points to cut the lead to 5. While the Ravens held a 5-point lead late in the game, the 49ers got it to the 7-yard line, pushing for the go-ahead touchdown. At about 2 minutes left, they turned the ball over on downs, and Baltimore went on to win. Does anybody remember that? No. Now we're down to one hand. We went from 3 fans to one that remembers the game. Well, what if I told you that this was the Blackout Bowl? Does that ring a bell now? So to add a little bit of color to the game summary I just gave you, Baltimore built a 28-6 lead early in the third quarter before a partial power outage in the Superdome suspended play for 34 minutes. The field had gone dark. After play resumed, San Francisco scored 17 unanswered third-quarter points to cut the lead to 5. So you see, this failure changed the momentum. It changed the direction of the game. Now, ultimately, I gave you the end of the story, and Baltimore did go on and win. But in the beginning of the game, it looked like it was a rout, and it was because of this failure that things changed. The public perception of that power failure, the failure of a large piece of public infrastructure, was that it had a huge impact on the game, even though not the final result. Another thing this did, though, is this pushed the topic of large engineering failures back into the media cycle for a little bit. It also caught the attention of James Hamilton. James Hamilton is the Vice President and Distinguished Engineer of Amazon Web Services. I had the pleasure of meeting James a couple times while he was at Microsoft Research, and I was a grad student at Berkeley. He was one of the industrial researchers that we always really loved to talk about our research with. It was always a little scary at the same time because he could just go right in there and pinpoint, exactly what we were missing and what we got wrong. But his feedback was always valuable. He also gives great talks. There was a talk at last year's reInvent that will leave your head scratching, and it looks like he gave a new version of that talk yesterday at reInvent. So read his blog and listen to his talks. It's great, and it'll really stretch your mind. So anyways, related to this topic, he wrote a blog post entitled "The Power Failure Seen Around the World." And in this blog post, he analyzes the power failure to identify the root cause. And in doing so, he outlined a fault mitigation framework that is valuable when studying events like this. Now, this is not a framework for software problems or for working in the cloud or for DevOps teams. This is a general framework for general engineering problems. What he wrote was, as when looking at any system faults, the tools we have to mitigate the impact are 1, avoid the fault entirely, 2, protect against the fault with redundancy, 3, minimize the impact of the fault through small fault zones, and 4, minimize the impact through fast recovery. This seemed really interesting to us. Avoid the fault entirely. Avoid it. Protect against the fault with redundancy. Mask it. Minimize the impact of the fault through small fault zones. Bound it. Or minimize the impact through fast recovery. Fix it fast. Now, at the time we ran across this article, we had been battling the gremlins at Stackdriver to try to keep our system running. And we felt like there was something we should learn from this, but we didn't quite know what it was. By the way, in this article, Hamilton concludes that the way the Superdome could have protected itself from this was to rent a few diesel generators that would have cost a couple $1 million. Now, that sounds expensive until you remember a 30-second TV ad cost more than that at $4 million. So like I say, it felt like there was something we should learn from that, but we didn't know what it was. Then the picture became more clear when we recognized the importance of fault domains in the cloud. A fault domain is a group of resources that share a single point of failure. Stated the other way, resources in different fault domains fail independently. Now, all of the major public clouds that are built today just happen to have similar concepts of what those fault domains are. At the smallest granularity, there's an instance, a single virtual resource, and that resource can fail independently of all others. At the biggest scale, there's regions. A region is a geographical area which often has multiple data centers in it. And the reason that's a fault domain is because there can be a large-scale power outage, there can be a hurricane, or there can be an earthquake that can take out that entire region. And then in between those two fault domains, there's a zone. A zone is a subset of resources in a region, and typically it corresponds to a data center. There's a fourth fault domain that's starting to emerge as new cloud providers are emerging as their viable alternatives. And this is the provider. We are seeing customers that are seriously talking about building their apps that span cloud providers in order to protect themselves against any lock-in or, quite frankly, people leaving the market. By the way, this figure here shows the data centers, their location and their relative size. This is all public information, but it's pretty hard to dig it all up. And it's a few months old now, but I think it's kind of illustrative of where the cloud providers are actually deploying their resources. So now we have these two ideas, and we put them together, and now we had something interesting. We crossed Hamilton's fault mitigation strategies with the cloud fault domains, and now we had a framework for discussing potential system faults, solutions, and their cost. At Stackdriver, we referred to these lovingly as the 4 Hamiltons. So how did we use this? Well, we would typically consider a component of our infrastructure. We would think about how a failure in each fault domain, that's the vertical axis, would affect the component in the broader system. And then we would debate about how we wanted to mitigate that failure mode. That's in the horizontal dimension. Now, the strategies on the right-hand side have a bigger negative customer impact than those on the left, but that doesn't mean we should just avoid every failure. You know that's not possible, and even if it was, it'd be far too expensive for us to actually undertake. So what this framework instead does is it gives us an explicit way to discuss the trade-offs between these two things. So let's look at each of these just briefly a little bit more. The first strategy is to avoid it. Formerly, this meant buying very expensive enterprise-grade hardware. Now in the cloud, we have no control over what hardware we have, and in fact, we've heard from many of the providers that they usually try to use the cheapest hardware they can. So instead, now this is about solid architecture and good software engineering. As far as specific techniques to protect against instance failures, it's not particularly new or exciting, but a lot of times it means writing good code and testing it thoroughly. It's also important to use high-quality components. Use the stuff that's battle-tested. When you're looking at web servers and databases, pick the stuff that other people have used and have had good luck with. This is not the time to use, Sideshow Bob's discount HTTP server that he used as a beginner project in some 24-hour hackathon to learn Erlang or something. I mean, that may be what all the cool kids are doing on the message boards, but if you want to build a system that's going to stand up, stick with what we know. For the larger fault domains, one of the best strategies is actually to let someone else handle it. Let someone else do the work to avoid the failures for you. We used a number of hosted services like RDS and ELBs from AWS, and of course they have failures going on under the covers. But to us and to our system, those appeared to be fault-free components. The second strategy is to bound it. Here we want to minimize the scope of the failure to reduce the customer impact. The most common technique here is sharding. And depending on how you shard, sharding can either protect against instance failures or zone failures or region failures, just depending on the size and the location of your shards. Another way to do this is to design different subsystems to be as independent as possible. And that way the failure of one subsystem or feature doesn't necessarily affect those of the other. And so if enough features remain online, your customers might not even notice that you're in a partial state of failure. And from their point of view, the fault has been perfectly bounded. The third strategy is to mask it, using redundancy or replication to avoid the fault. This is a lot of where those core distributed systems concepts and cool research results that you read about can be applied. These approaches are also can protect you against instances or zones or regions depending on kind of how they're configured and implemented. A lot of time, some of these include using pools of pools of peers and workers handling similar work, master-slave or primary-secondary replication, or clustering, quorum, gossip, and peer-to-peer protocols. Some of the services that we talked about earlier, those hosted services that can be fault-free from our point of view, and they're failing under the covers, are actually using a lot of these strategies in order to look stable to us. And the final strategy was to fix it fast. Sometimes this is the best approach, but if you're using it too often, you're doing it wrong. Now, some examples of this for instances, if you push bad code, the quickest thing is to fix it fast. Just revert the bad code and repush it to fix the instances. If you corrupt a resource, the cloud is elastic. There's more there. Just blow that instance away. Excuse me. Just blow that instance away, provision a new one, and deploy code to it, and get on with things. Or if you have some state you've lost, just restore it from a backup. Whatever it is, whatever you plan for, and those plans come from debating the strategies in that framework that we discussed earlier, you have to plan for it and you have to document it. And you have to practice it. You do practice these things right. I mean, that's very important. This comes down to gaining that mastery of your system. And you should practice that when you're awake and when you're alert, so that when you're half asleep at 3 o'clock in the morning, you can still do it. Part of being able to do this in a repeatable fashion is to have automation in place to do that. So we first talked about a healthy and productive view of risk-taking. We just talked about the 4 Hamiltons and how they can frame a discussion for our systems about how they fail and how we might want to mitigate those failures. And understanding that is like a good safety net that we now have under us for when we want to start undertaking these risky behaviors. Finally, I want to share some examples from Stackdriver, talk about how we took risks to improve our system, and I'm going to focus on how we tried to do things cheaply. I think this is an angle that is not discussed much, but for a startup trying to build a big system on a shoestring budget, this is important. There are several dimensions to being cheap. There's money, there's time, and there's engineering investment. The way we were able to do experiments so cheaply, in general terms, is to use our production system as much as possible with just a few resources for the extra tests that we were trying to run. We have one funny anecdote we like to joke about at from our Stackdriver days related to cost. When we were just getting started, Dan Belcher, one of our founders, who was serving largely as a product, and one of his many hats was a product manager role, set a CloudWatch alert, an AWS CloudWatch alert on cost to tell him when we spent more than $1,500 in a month. And for the first few months when we were very tiny and we were just trying to get to MVP and so on, that alert didn't fire. And then after a few months, it fired on the 28th. And then it fired on the 23rd. And then it fired on the 15th. And somewhere along here, the alert was no longer important to us because we had better ways to track our resource usage and our costs and things like that. But the alert was never deleted, was never removed because, well, that stuff happens. And it became that noise that we've been talking about in so many other sessions about all these alerts that we get that we just learned to visually filter out. So the alert was never deleted. But we're always reminded because on the first of the month before Dan wakes up, he still gets that alert. And so that's how we know that our account is still active. All right, so if we're going to dig into some examples, I need to explain a little bit about our system. At a high level, there's many characteristics of the Lambda architecture that is, again, typical of so many systems that we build today. Some of the key components of that system is the data collection subsystem. These are components that are querying the cloud provider APIs to collect the monitoring data that we want to manage. There's the ingest pipeline, which is responsible for archiving and indexing all those messages that we collect. The alerting subsystem, we have a custom alerting subsystem, which evaluates user-defined policies on that data and notifies our customers if their system is out of policy for some reason. There's batch processing, which we use for an aggregation and analysis. And there's a UI, which is particularly strong, has particularly strong graphing and visualization capabilities. And all of this is backed up with a lot of custom automation that we have for this. As far as the technology stack, we're a Python shop. We use Django and Angular in the front end. For data stores, we use Cassandra, Elasticsearch, and MySQL. We're heavy users of RabbitMQ, as we'll see in the next slide or two, and we use Puppet for configuration management. We have several hundred instances running in AWS. We have about 50 deployable units, and we push code to those dozens of times a day. So we have 12 engineers. If we're doing dozens of times a day, that means your average engineer is pushing, multiple times a day, maybe, 5 times a day on average or something like that. So to dive deep now, let's consider one of the more challenging parts of the system to test, the ingest pipeline. It's responsible for taking data off the wire and getting it where it needs to go. Now, in this case, data can mean several things. It means the inventory of virtual resources that a customer has that we need to monitor. It means the metadata about those resources. It means events that are describing changes in the customer's environment. And it means measurements, the actual observations at various points in time of those resources. Now, those measurements can come from multiple sources. There's the cloud providers that come from our collection subsystem that's querying those APIs. There's measurements from agents, which the customer can deploy within their instance, which gives us a view into their infrastructure from the inside. There's custom metrics. There's an API that customers can instrument their software with to give us whatever metrics they're interested in. The humidity of the soil in the plant in the lobby or whatever else, the number of people logging onto their website. And then endpoint probes, which are spread across the globe, measuring the performance of their service from the outside. There's a set of components that are working together in order to handle these messages, to get these messages where they need to go in the ingest pipeline. Messages come in the top to a component we call the gateway, which does the message validation, and then post that message to a message broker. This is the Rabbit instance that I referred to. And then there's a number of consumers that are pulling some subset of messages off of that broker. The archive is pulling all of the messages off and storing them in S3. This is our gold copy of the data. The alerting component is pulling off a subset of measurements that need to be referred to in order to compute alerts and pushing those through the alerting pipeline. And then there's the indexing piece, which is pulling off certain messages and getting them to Cassandra or Elasticsearch as is appropriate. This set of instances is, we put a lot of effort into being able to tolerate instance failures at the instance fault domain here. You can see that the components are all strongly decoupled with the message broker between them. There's also multiple points of buffering in the implementation, so if anything goes down, we have ways to recover that data. So the previous slide showed the set of components we needed to process a single message, but we have to scale up to process billions of messages. And the way we do that is we draw on the ideas of the cell architecture. A cell is the set of components that are needed to process a single message. That's what we saw on the previous slide. It is the unit of scaling. So when the cells that we have deployed become too busy, the load becomes too high, we can add scale by deploying a new cell. Each cell is independent from all the other cells. So if a failure in one cell happens, all the other cells continue to operate. And all of the components for a single cell are deployed in the same zone. So that allows us to tolerate zone failures in addition to instance failures. If one zone goes offline, we lose the set of cells in that zone, but all of the cells in the remaining zones stay online. Now, because of the importance of the cell to our design, a lot of the automation that we've built is related to the cells. So this idea of the cell is how we scale out our portion of the system here. But I talked about the downstream systems, the data sinks, which is Cassandra and Elasticsearch and so on. Those use their own techniques in order to scale up. Cassandra uses the peer-to-peer ring, and Elasticsearch can cluster and so on. So we have an architecture for an ingest pipeline that we're pretty happy with, and we have an approach for scaling it with the cells, and we have automation to help operate it. But it is not a static asset. We continue to make changes to this day, and we continue to push those changes to production. We obviously have to be careful here, though, because if we screw up, we end up with a big pile of messages spilled on the floor, and it takes a long time to mop them all up. We also can't just pause the ingest pipeline. Those messages keep coming 24/7. This is a machine-generated load that is nearly constant. at all times of the day. And we also can't schedule maintenance. The customers, just don't stand for their monitoring system to go offline for a bit. So this makes dealing with our ingest pipeline more like changing the jets on the engines on a jet airplane while it's traveling at 30,000 feet in the air. We have to do all of this online without any downtime. Now, when we make these changes to the pipeline, we typically think about the change and verify the change in 3 dimensions. And these correspond to the three V's of big data: variety, velocity, and volume. I think it was Gartner that originally offered this characterization related to big data. We use it here for our system. Big data is a pretty big buzzword right now, and I don't know exactly what that means, where it becomes big. But I'm pretty confident Stackdriver is operating at least medium data terms right there, where we are today. So as I said, I want to focus on how we test along those 3 axes: variety, velocity, and volume, but how we can do it cheaply at the scale of a startup. We can't simply deploy one of everything. We don't have the resources for that still to this day, because it's not just money. Even though we have the Google backing now, you could argue that we have enough money. But we still have that small set of engineers, and we just can't handle the operational overhead of dealing with that. So what do we do? All right, the first dimension is variety. For these tests, we don't care so much about how fast the messages are arriving. We just want to make sure that we see a representative sample of the messages so that we're pretty confident that any change we make handles all the usage modes. A lot of this data is user-generated data, and we can create a lot of tests, but ultimately it comes down to what the user is sending us. Now, it just so happens, we talked about earlier when we were talking about the cells, that we know that the production system is creating archives of every message it's ever seen. So that provides a great source of data to test for all this variety. So what we do here is we have our production system running in one account. We have a test system. We stand up a single instance of the component that we're interested in testing, and then we replay as much data as we want from the archive. We can continue to throw data at it until we're pretty confident that we've seen enough data to be confident that we can handle what it's going to give us. Now, the cost of this kind of test is to provision and deploy just a single resource, the new version of the resource that we want to test. And this works for any component in the cell, including the gateway, which is the validator. The data comes from S3, so we're actually not touching the production system at all. We get to use the production data, but we're not perturbing the pipeline at all. And of course, when we're done, the cleanup is really easy too. We simply wipe that instance away, and we know either it worked or it didn't, and if it did work, we can go on to the second phase of testing. The second phase of testing is for velocity. Here we start to get a little bit more concerned about speed. We want to make sure that the changes that we make to one component in the cell don't have the impact of slowing the cell down. We want to make sure that we need roughly the same number of cells before and after a change, unless we're intentionally making a decision to slow it down, to change the capacity because of a change, to change the scale-out factor because of a change. So here we want to run the cell at full speed to see if it can support the load of a production cell. And to do this, we rely on a feature of RabbitMQ called federation. Federation allows us to forward messages from one broker to another. So here we have a cell operating in our production environment, and in our test environment, we set up another gateway cell, which contains the Rabbit node. And then if we're not testing the gateway, but another cell or another component, we set that component up as well. So the cost of this is 2 nodes, which is, again, very easy for a single developer to set up and get ready to go, especially with our automation. Then we turn federation on, and we see if it's able to keep up. Now, this type of testing does add a little bit of load to our production infrastructure because forwarding all these messages doesn't come for free. But only one cell is impacted out of many. So there's a slight overhead to a single cell in the architecture. So the impact is relatively low. And again, when the test is over, we turn off federation, we throw those 2 instances away, and at that point we've verified that any change we make can indeed support the speeds that we need it to support. Which takes us to the last phase, the last V, which is volume. And so sometimes, depending on the change, we require that we be able to test a change at full volume. This is often used when we need to make a change to one of our data stores. There have been multiple times when we've replaced our Cassandra cluster, either because we go to a new instance class, or we want to experiment with the new SSDs, or we change some configuration setting like the compaction strategy or something like that. Before we put all of our, push all of our load, our read load to that new instance as well, we want to make sure that it can stand up and support the full load. We've also used this approach when we migrated to our new alerting system. We rewrote the alerting system at one point, and we used this approach so that we could run both the old and new in parallel for a while to gain some confidence in that. So what we do here is first we set up the new data sync, like a new Cassandra instance that we're interested in testing. Then we add a component to each cell that targets that new backend. And because of the strong decoupling we have within a cell, the other components in the cell really don't even know we've made this change. When we're ready, we have that new component subscribed to the message broker. Messages start flowing through and into the new backend. We can turn up the volume incrementally. We can start this load flowing in just a few cells at first before we turn it all the way up. And so at this point, we can have the full load going against both old components and new components simultaneously. The amount of extra load on the system is, or the amount of extra resources required here is the size of the new Cassandra ring, which is fundamentally what, one of the things we're trying to test, and one new instance in each cell. So again, it's pretty incremental. If the change works out, what we typically do then also is we perform a backfill operation in order to get all the historical state into the data store, and then we can start tearing down, which means pulling all of the components that we're replacing. If we're replacing the indexer, we pull the old indexers out and decommission the new data store. And with that approach, with using just a few extra resources at any time, we're able to change the jet engines while we're in the air. So this approach has worked pretty well for us for a number of different kinds of changes and a number of different times. There have been some challenges, especially getting it up and working the first time. Access control is a big one. We don't have the kind of privacy problems that you have if you have credit card information or any real personally identifying information. But our customers are still curious about where their monitoring data goes, and we want to make sure that's protected. So we need to make sure that it's only the test environment. Outside of our production environment, only the test environment has access to that. And so that involves a lot of cross-account IAM setup, which if you've ever played with is a little fiddly to get working the first time. Also, we want to make sure that we can only read from the data stores in production and not write to them, so that any of the testing we're doing doesn't have unintended consequences of changing our state in production. Relational data, which is something I haven't talked about here, the configuration data gets accessed a fair amount. Again, there's that cross-account ACL problem to speak of. And then if there's any minor changes, config changes that happen as part of the test, we have to make sure those are isolated. So it often means snapshotting portions or all of databases over to the test system so we can do that. And then finally, it keeps coming up, automation. It's one thing to be able to do this manually, but we have to make this turnkey so we can perform any of these tests on our own. So with that, that's what I wanted to share today. Hopefully between Gene's talk this morning and my inadequate mumblings earlier, You understand why risk is important, and taking risks is important for improving your product. And we talked about the 4 Hamiltons, which is a way to be very explicit about risks and mitigations for the systems that you're working on. And then lastly, some of the ways that we approached risk-taking and experimentation in Stackdriver from a cost-conscious point of view. And I think with that, I am open to taking questions with either my Google hat or my Stackdriver hat. So. I don't know. Where are we supposed to put our slides? I'm happy to put them wherever. I don't know if the organizers are collecting them. If not, I'll make them available somehow. They. I send the slides to USENIX.org, or that's how they ask for them?
Actually, an email address is, send an email to slides at USENIX.org.
Okay. So you can send an address to slides at USENIX.org, or here's an email address that you can. Oh, I send them there. Okay. You can also email me.
Why am I shouting? Yeah, just slides at usenix.org, and they'll post them to the website.
Okay.
Probably at this point tomorrow, but the sooner you get them there, the sooner they go up.
Okay.
Thanks. Any questions? Got a couple of minutes? Going once? Going twice? Do I see a hand?
Oh. Sure.
Oh.
Talked about federating the messages to a component downstream.
Yep.
Right, to test volume or velocity.
Yep.
What if you're not, brokering messages around and you're looking at, for example, HTTP traffic, and you're thinking about, can my test environment handle the velocity that's coming into production?
Yeah, I think that's a good question. I think you probably want to look at what kind of forwarding your server or your proxy has. I'm not actually as familiar with those features of those tools as I am with the message brokers. I don't know if anybody else has ideas related to that. HA proxy with mirroring, he says.
You can also record traffic and resend it if that's possible. Either take a sample of real traffic, especially if it's read traffic, and just replay it a lot, or make a synthetic benchmark, or you can just test in production with really good error reporting, which is what we do.
Recording the data is is similar in spirit to what we're doing with our archive. Instead of just recording the JSON objects, which is what we do, actually recording the full kind of HTTP level traffic.
Microphone's back on the stand now.
All right. Thank you.